All right. We were talking about how as things get colder, they contract, and they get warmer, they expand. And we said one of the exceptions to that is water. But that should come with a provision. Actually, water behaves according to that rule most of the time also. All right. And here's the deal. If we look at a graph here, let me see if this can show what I want to do. More about this one up here, but basically, as water gets colder, its volume gets less and less and less, but it gets the very densest. Okay, its volume gets less, it's getting smaller and smaller and smaller. It's contracting as it gets colder, which means it's making it more dense. All right. But at 4 degrees Celsius, that's still above freezing, just barely, but it's above freezing, okay, that is where it is the most dense. But that's where things start happening. When ice crystals begin to form, when we measure temperature and say it's 4 degrees, that's the average. Some of them are getting colder, and some of them are actually starting to form ice crystals. Okay, here's your water molecules. Here is when they start joining together to make ice. They form a lattice, and it forms this framework which pushes the atoms farther apart than they were when they were just liquid water. So now they're farther apart, they're less dense, and so as some of the water over here starts to freeze at around 4 degrees, it begins to make the whole water sample slightly less dense. Okay, and so it becomes less dense, less dense, less dense, and by the time it gets to 0, it's actually less dense than it is at 4 degrees. I'm sorry, I did that wrong earlier. As we're coming down, it gets colder and colder. It gets less and less, more and more dense. As it contracts more and more, and it gets the most condensed here. And then, but once it freezes, it's actually beginning to get lighter because now they're pushing each other apart to make this lattice until eventually the whole thing forms ice, and now you have this whole lattice over here, and it's all lattice. And because of that, it's less dense. The space in here is a vacuum. There's nothing in there. Okay, if there were other molecules in there, then their mass would make it more dense again. Okay, so it actually takes up less space, and so ice is going to float. Okay, so water is its coldest density at actually 4 degrees, and when it gets down to 0, because of the ice starting to form in here, it's becoming less and less dense. And at 4 is where some of those ice molecules are going to start forming. Because even though the average temperature of the water sample is 4 degrees, some of those individual molecules are going to be colder, just like some are warmer, and they're going to start forming ice crystals. All right. Now, well, that's neat, that's great, but why is that important? Okay, well, let's see. Say we go to a pond now. All right. And so we're going to a pond. Where's the coldest? Where's it going to be coldest in the wintertime? Well, up touching the surface, because the surface of the pond, let's pretend this doesn't have ice on it yet, okay, is negative 10 degrees. It's below freezing outside, okay? And so heat from the water is going to escape into the air until the equilibrium, but they're probably not going to because you have a small amount of water and a humongous atmosphere up here. And so heat is going to flow out of the water. Now, as the water gets colder and nears 4 degrees, it gets denser, and therefore it's going to sink, okay? And so it's going to sink. And so all this water starts sinking as it gets more dense. But as it goes colder than 4 degrees, but if it gets that before it sinks, it begins to form ice crystals, which make it float. And therefore we get a sheet of ice up here. Now ice becomes an insulator, okay, and it keeps the water underneath it from touching this colder air up here. And so it stops that flow of heat, it insulates it, and it keeps this temperature in here. It's going to be somewhere around 4 to 0 degrees. It's going to be very chilly, yes, but it's not going to actually freeze. And that way fish, frogs, and other critters that live down here, some of them burrow down at the bottom. Even though it's going to be very cold water, it's never going to completely freeze. And since ice is less dense, it floats on top. Now, if ice were more dense, just like most things, when they become solid, they get more dense, then this ice would float to the bottom, sink to the bottom. And then new water up here would lose its heat, and it would turn into ice, and it would sink, get more dense, and sink to the bottom. In most substances, when they turn from a liquid to a solid, they're going to be more dense, and they're going to sink. And therefore, ice would sink. Ice is an exception to that because it makes that lattice work where we spread the atoms farther apart, they're less dense, and it actually floats. That's why ice floats in your cup that you're drinking, like I've got one over here with ice in it, okay, it's floating in that. And it's important for critters that live in a lake, because if you live somewhere where the temperature above here is freezing, okay, then it allows the ice to make an insulating layer, and organisms down here in the water can survive. All right. All right. Now we said heat is when the thermal energy moves from hotter objects into colder objects. That's what heat is. And so let's talk a little bit about how that happens. How does heat transfer? Okay. And basically, if we look at this example right here, okay, we have all three types. The first type is by conduction. If you touch the metal on here and it's touching these atoms here, it will pass the heat along to the handle. That's why most cast iron skillets, either you have to use a little pot holder thing on the handle, or if you have other types of, a lot of times they'll have some type of plastic handle that will not conduct and will not touch it. But if you have a metal handle, the metal in here touches the atoms here, touches these atoms here, and they touch these atoms here, and then they touch your hand. And so when two objects touch, we say that they have transferred their heat by conduction. All right, conduction just means that two objects have to actually touch. If you touch a hot, you grab something hot with your hand, a hot beaker, and you drop it, that was conduction. You were touching it. Okay, radiation is when heat travels through air or even a vacuum from one object to hit another object. For example, you would feel some warmth on your hand right here, and that would be from radiation coming off the flames. You're not touching the flames, but you can feel the heat radiating across to your hand. The heat is also radiating up into the bottom of this pan. Then it heats up the metal. The metal touches the water, which would be conduction, and therefore begins to heat up the water. So you want a metal pan that is a good conductor so that it carries the heat that it catches from this. Now if it were sitting on the flames, that would be conduction if it were touching flames, or if you had like a stovetop where it's touching the stovetop, then that would be conduction. Conduction from the metal into the water. But once it gets in the water as it heats up, it begins to, the particles move faster, they become less dense, they spread out, and they begin to rise. And then they begin to cool off up here, and they sink, and they make a little, what we call a convection current. And now the molecules within the water are moving around, and they're spreading the heat because the actual heated molecules are moving around. Convection is going to occur, you're going to have to occur in fluids because they have to be able to move around, okay? And so therefore the water here. Another example up here is if you have this box, if you have in a room, so this is a room, we used to have wall radiators where they had steam going through them, and they would release the heat would rise. As it rise, it would cool off, and then it would become more dense, and it would begin to fall, and then it would come back over here. As it touches the radiator, it would get hot, the molecules would spread farther apart, it would rise, and it would come up. On a similar scale, this is what happens out in nature. Okay, when you have wind, basically you have hot air rises, then it cools off, then it gets more dense, it sinks down, and if you were down here at the bottom, you would technically feel some wind going across here. All right. Now, if you live near the ocean, they have what they call land breezes and shore breezes. Okay. During the day, it gets hotter on the land, and so it heats up, the air rises, that pulls air from the cooler ocean over here, and so you have a sea breeze, and the sea breeze brings cooler air in. As it comes over the land, though, it heats up and it rises, and you have this cycle going around. All right. At nighttime, it gets colder on land, but the water, remember, has a high specific heat, so it cools down slowly, so it stays warmer longer. So now the warmer water is rising above the ocean into the sky. That pulls the cooler air from the land out here, and so now you have a land breeze. Okay, notice that either way you have cooler air moving in or cooler air moving out, and so it kind of keeps on the shore. They tend to have, they don't have as big a temperature fluctuation as you would if you were surrounded all by land. Okay, and so yeah, but you basically see how convection currents cause these breezes, and on a bigger scale that happens anywhere on Earth. You have high and low pressure areas, and you have high caused by temperature changes, and air rises and sinks and rises and sinks, and if you're in here, that's where you feel the prevailing wind going a certain direction. So just to recap real quickly, if your two objects are touching, that's conduction. If it's radiating through space or a vacuum, like the sun goes through outer space where there's nothing, but it radiates till it hits us and it releases that energy. Or if it's in a fluid, it can move the fluid around. The hotter fluid will move around, rising as it heats up and gets less dense, cooling off and sinking as it gets more dense. And the actual fluid moves, either gases like in the wind or like boiling water. When you see bringing water to a roiling boil or a full boil, that's because you're seeing that little convection cycle going on inside your pan. Alright, and there's one, now that's the three ways of heat transfer: conduction, convection, and radiation. But let's talk about something else that's kind of related to this. The amount of pressure when air either spreads out and expands, or when it's compressed, it can change the temperature of it also. Just as a very simple thing, if you lightly breathe out on your fingers, you will feel that the air is warm. But the very same air coming from your mouth, if you blow hard on it, you will notice that it feels cool. Alright, so basically when you blow, you kind of puff up your cheeks, you put more pressure on it, and as the air has more pressure on it, it comes out through your mouth. It's expanding because there's less pressure once it comes out of your mouth, and as it expands, it cools off. So when you blow the air, it always feels cool. Now if you can breathe it out gently, where it's at the same basically as it was before, it's warm like it was before. So basically, if you compress air, it heats it up. If you let it expand as it comes out, it will cool off. For example, if you are using a propane grill, especially if it's cold outside, as the air or the propane is coming out of the tank, it's expanding and it cools off. The air inside the tank is also expanding because there's less air, so what's in there can spread out. And as it expands, it cools off, and a lot of times you may actually have ice forming on the outside. If it's a cold wintertime, you may actually have ice start forming on the outside of your propane bottle, because as it cools off, it takes heat from the air to flows into that colder area, and it can actually freeze the water vapor in the air around the propane bottle. This is also the same general principle that your refrigerator works. It has a compressor. As it compresses the air, it heats up, and you'll notice there's heat coming out the valves on the back of your refrigerator. As it goes, as the fluid in it, coolant, comes out of the compressor, it expands, it cools off. So as it goes through your freezer and your refrigerator, it's cool, and it soaks up any heat from your refrigerator, okay? And then as it goes back into the back, as it's compressed again, it gives off heat off the back, and then it is let go into your refrigerator again. It expands, it cools off, and as it goes through, it picks up, since it's cold, that causes heat, any heat trapped into your refrigerator to flow into the fluid or your coolant, okay, Freon, whatever you have in your refrigerator. And the same thing happens with a heat pump, which people use for their air conditioners. Okay, we talk about air conditioners, but actually a lot of them are what we call heat pumps. The same thing, by compressing the air and then letting it expand, it causes this coolant, special kind of coolant that really changes the temperature a great deal. And as that coolant flows through, it soaks up the heat. All the heat flows into it because it has a lower temperature than the refrigerator or your house if it's a heat pump, and therefore, and then when it comes back, it's compressed again and uncompressed, and you keep doing that over and over, and just it's a cycle of soaking up the heat in the refrigerator, letting it out the back as it gets recompressed, and then it soaks up the heat again as it comes through, which makes air conditioning work. But this time of year is a very, very important thing. Alright, now we have just a few things to talk about. Radiation a little bit I want to talk about, and changes of phases, and then we'll be through. So one more video and we'll be done.